Download this code from codegive.com, link in the description below. Apple, Safari, and that pesky memory leak, a deep dive and hypothetical fixes. Safari, Apple's flagship browser, is often lauded for its speed and integration with the Apple ecosystem. However, a recurring and persistent issue has plagued it for years: memory leaks. These leaks can lead to sluggish performance, browser crashes, and even impact overall system stability. While Apple has addressed several instances in the past, the problem tends to resurface, hinting at underlying architectural complexities. This tutorial will delve into the nature of Safari's memory leak problem, explore potential root causes, examine real-world scenarios where it manifests, and propose hypothetical solutions, with code examples where applicable, that Apple developers could consider. It's crucial to understand that this is a speculative analysis. We don't have access to Safari's source code. However, based on observable behavior and common web development practices, we can infer potential problem areas. 1. Understanding memory leaks, the fundamentals. Before diving into Safari specifics, let's establish a firm understanding of memory leaks. In programming, memory leaks occur when dynamically allocated memory is no longer needed by the program but is not released back to the system. This unused memory accumulates, consuming valuable resources and potentially leading to application instability. Here's a simplified analogy: imagine you're constantly renting storage units to hold items you no longer need but never cancel the rental agreement. The units fill up, costing you money, and eventually, you run out of space to store new, essential items. In the context of a web browser, memory leaks can arise from circular references when two or more JavaScript objects hold references to each other, preventing them from being garbage collected even when they're no longer in use. Detached DOM nodes DOM elements that have been removed from the visible page structure but are still being referenced by JavaScript code. Unclosed timers and intervals set timeout and set interval functions that are never cleared using clear timeout and clear interval continue to execute code, potentially retaining references to other objects. Event listeners that are not properly removed from DOM elements when those elements are no longer needed. Caching issues improper caching strategies that retain excessive data in memory. Native code leaks leaks originating from the browser's underlying native code, written in languages like C++ or Objective-C, particularly within its rendering engine, WebKit, or JavaScript engine, JavaScript Core. 2. The Safari memory leak problem, symptoms and manifestations. Safari's memory leak problems often present in the following ways. Gradual slowdown as you browse the web, especially with multiple tabs open or by visiting complex websites, Safari's performance degrades noticeably. Scrolling becomes less smooth, page loading times increase, and the browser feels sluggish. High memory consumption monitoring. Safari's memory usage in Activity Monitor, Mac OS, reveals that it's consuming a disproportionately large amount of RAM, even when idle or when the number of open tabs is relatively small. Browser crashes. In severe cases, the memory leak can exhaust available RAM, leading to Safari crashing or even causing the entire system to become unstable. Specific website triggers. Certain websites, particularly those with heavy JavaScript usage, complex animations, or frequent AJAX requests, seem to exacerbate the memory leak problem. WebKit web content process issues. The WebKit web content processes, responsible for rendering web pages, often exhibit high memory usage. Multiple of these processes can contribute to the overall memory drain. 3. Potential root causes in Safari's architecture, speculative. Given Safari's reliance on WebKit and JavaScript core, let's examine potential areas where memory leaks might originate. WebKit's rendering pipeline. WebKit's rendering engine is responsible for parsing HTML, CSS, and JavaScript and transforming them into visual content. Leaks could occur within the engine's layout, painting, or compositing stages. For example, improperly managed textures, retained shaders, or unreleased graphical resources could contribute to memory bloat. JavaScript Core's garbage collection. JavaScript Core, Safari's JavaScript engine, employs a garbage collector, GC, to automatically reclaim memory occupied by objects that are no longer in use. If the GC has difficulty identifying and collecting certain objects, example due to circular references or native object interactions, memory leaks can occur. Additionally, overly aggressive caching within the engine could contribute. Bridging between JavaScript and native code. Web browsers heavily rely on communication between JavaScript, running in the browser's sandbox, and native code, example WebKit C++ implementation. Errors in managing object lifetimes or releasing resources during these interactions can lead to leaks. For instance, if a native object is created in response to a JavaScript call but is not properly released when the JavaScript object is garbage collected, a leak occurs. Extensions and content blockers. Third-party extensions and content blockers can sometimes introduce memory leaks due to poorly written code or conflicting interactions with Safari's core functionalities. Caching strategies. Safari employs various caching mechanisms to improve performance. While caching is generally beneficial, an improperly implemented cache can lead to leaks if it retains outdated or unnecessary data in memory. 4. Code examples and hypothetical fixes. Illustrative. It's impossible to provide definitive fixes without access to Safari's source code. However, let's explore hypothetical scenarios and potential solutions that Apple's developers could consider, with illustrative and simplified code examples. A. Circular references in JavaScript *. Hypothetical fix *. B. Unclosed timers / intervals *. Hypothetical fix *. C. Unremoved event listeners *. Hypothetical fix *. D. Detached DOM nodes *. Hypothetical fix *. Weak maps, JavaScript feature to mitigate leaks related to DOM elements. Hypothetical fix F. Native code and JavaScript interaction *. Imagine a scenario where a JavaScript API calls a native WebKit function to create a graphical resource, example a texture for a WebGL canvas. Hypothetical fix *. Resource management via ownership * implement clear ownership semantics. The native code should explicitly track the life cycle of resources it creates. If the corresponding JavaScript object is garbage collected, the native code should automatically release the associated resources. This often involves using techniques like smart pointers, example std unique _ptr or std shared _ptr in C++, to manage memory automatically. Reference counting * use a reference counting mechanism to track the number of references to a native object. When the reference count reaches 0, meaning no JavaScript objects are referencing the native object, the native object can be safely released. Weak references * consider using weak references from JavaScript to native objects. A weak reference does not prevent the garbage collector from reclaiming the native object's memory. Garbage collection integration * design the native code to be aware of JavaScript core's garbage collection process. Implement callbacks or notifications that are triggered when JavaScript objects are garbage collected. This allows the native code to release associated resources in a timely manner. 5. Strategies Apple might employ for detecting and fixing leaks. Apple's engineers likely utilize a multifaceted approach to identify and address memory leaks in Safari. Static code analysis. Employs static analysis tools to scan Safari's source code for potential memory management errors, such as double freeze, dangling pointers, or leaks in native code. Dynamic analysis and profiling. Use dynamic analysis tools, example instruments on Mac OS, to monitor Safari's memory usage during runtime. These tools can help pinpoint specific areas of code that are allocating memory but not releasing it. They can also track object lifetimes, identify circular references, and detect memory fragmentation. Heap analysis. Analyze Safari's heap, the region of memory used for dynamic allocation, to identify objects that are consuming large amounts of memory and are not being garbage collected. Fuzzing and stress testing. Subject Safari to fuzzing, randomly generating inputs to test for vulnerabilities and crashes, and stress testing, simulating heavy workloads and prolonged usage, to expose memory leaks that might not be apparent during normal operation. User feedback and bug reports. Actively monitor user feedback, bug reports, and crash logs to identify recurring memory leak issues. Specific websites or usage patterns that consistently trigger memory problems can provide valuable clues. WebKit testing infrastructure. Leverage WebKit's extensive testing infrastructure to perform automated memory leak detection on a regular basis. 6. What can users do in the meantime? While we await potential improvements from Apple, here are some strategies that users can employ to mitigate Safari's memory leak issues. Close unused tabs. Reduce the number of open tabs, especially those containing complex websites or applications. Restart Safari periodically. Close and reopen Safari to clear its memory. Disable or remove extensions. Try disabling or removing extensions to see if they are contributing to the problem. Clear caches and website data. Regularly clear Safari's caches and website data. Safari-preferences-privacy-manage website data, to remove potentially stale or corrupted cached content. Update to the latest Safari version. Ensure that you are running the latest version of Safari, as Apple often includes bug fixes and performance improvements in updates. Limit heavy website usage. If you know certain websites are problematic, try to limit your usage of them or consider using alternative browsers for those sites. Monitor Activity Monitor. Keep an eye on Safari's memory usage in Activity Monitor. If you notice it creeping up excessively, take steps to reduce its memory footprint, example closing tabs, restarting Safari. 7. Conclusion, a call for proactive memory management. Safari's memory leak issues highlight the importance of diligent memory management in complex software systems. While it's challenging to eliminate all memory leaks completely, a proactive approach that combines careful coding practices, rigorous testing, and advanced debugging techniques can significantly reduce their occurrence and impact. For Apple, addressing these issues likely involves a combination of code reviews. Implementing thorough code reviews with a focus on memory management best practices. Automated testing. Expanding automated testing to cover memory leak scenarios. Profiling and optimization. Continuously profiling Safari's performance to identify areas where memory usage can be optimized. Transparency. Improved communication with developers and users regarding known memory leak issues and planned fixes. By prioritizing memory management, Apple can ensure that Safari remains a fast, reliable, and enjoyable browsing experience for its users. And hopefully, this in-depth exploration has shed some light on the complexities of the problem and potential paths to resolution. The key takeaway is that vigilance, rigorous testing, and a deep understanding of memory management principles are essential for building stable and performant web browsers. Remember that the code examples and solutions offered are hypothetical and serve as illustrative examples of the types of strategies Apple could be employing.